Okay, so this is a lecture on chapter 20, and yeah, I forgot to record it, so I'm going to record over this part, and then I'll try to add it to the part that I remember to record and try to make a coherent video. So anyway, I'm going to share the screen and start going through chapter 20. Okay, so the first part is I'm looking at the different kinds of combinations of acids and bases for a neutralization reaction. If I take a strong acid and a strong base, they completely react. It's a one-directional arrow. The reaction goes to completion. That's a titration problem. We cover that in chapter 17 and in chapter 19. If I take a strong acid and a weak base, the strong acid is enough to make it go to completion, and again we have a titration problem. We have a weak acid and a strong base. The strong base makes it go to completion. Again, that's a titration problem. But if we have a weak acid and a weak base, neither one is strong enough to make the reaction go to completion. It goes to the point of equilibrium. And so these are buffer problems. So a buffer is a combination of a weak acid and a weak base. So that's what buffer systems do. They resist changes in pH. They don't stop it, they just resist. So water is unbuffered. So here's a solution of water. If I add some kind of hydroxide into the water, I directly affect the concentration of hydroxide. That affects the pOH, pH, everything. Same thing with acid. If I put, say, 0.1 molar of a strong acid into this solution, I get 0.1 molar of this, and the pH would go all the way down to pH 1. Negative log of 10 to the minus 1 is 1. So there's absolutely no buffering here. But if I have a buffer solution, which is made up of a weak acid and a weak base, what happens if I put the hydroxide in there? Instead of directly affecting the concentration, some of the weak acid will react with it. The weak acid gets converted into its conjugate base instead of just having hydroxide in the solution. Same with the acid. I drop some acid in there. It reacts with the weak conjugate base. It gets converted into some of the weak acid instead of directly affecting the pH. So this solution is buffered. And notice, if I wanted a good, well-buffered solution, it would make sense that this concentration would be high and this concentration would also be high. So that's known as buffering capacity, and that'd be the best when these two are at equal concentrations. So, which of the following would make a good buffer pair? Hydrochloric acid and potassium nitrate. No, because this is a strong acid. And this, why would that be called a very weak base? It's because its conjugate acid, which would be nitric acid, is also on your list of strong acids. So its conjugate base, which would be nitrate, would be an extremely weak base. So what about B? Here's bicarbonate and hydrogen carbonate. They're both weak. Here's the weak acid, here's the weak base. So that would be a good buffering system. Hydroxide and HCl, no. That's strong acid and a strong base. Here's a strong acid and a weak base. What would that do? Okay. Strong acid and a weak base, that goes to completion. That would be a titration problem, not a buffer problem. But here's a weak acid and here's a weak base, so that would work. Here's water, which cannot buffer anything. And whether you want to call that a weak acid or a weak base, it would directly affect the water. The water can't buffer, so that's not a good buffering system. So anyway, there's only one calculation in this chapter, and that's going to be calculating the pH of a buffered solution. So I'm going to just cut to the chase and show you how to solve that problem. So what we're going to do is base everything on the acid. Okay, so we have to figure out which one is the weak acid and which one is the weak base. So I take the acid and I dissolve it into water. Okay, that's something we had to learn from chapter 19. And then we take the equilibrium constant for that, also known as the Ka, products over reactants. Also something we learned in chapter 19. And what do we really want? We want to get the pH. So we need this value right here. So all we're going to do is take this expression for equilibrium, algebraically solve for the hydronium ion. And then all we have to do is input the numbers. To get this, I would need the Ka, concentration of the acid, the concentration of the base. And to get the pH, simply the negative log of that value. Some problems are not going to give you the Ka directly, they're going to give you the pKa. So in that case, you also learned in chapter 19 how to convert the pKa into the Ka using this mathematics right here. So if we look at the expression for Ka right here, or right here, there's 4 variables. We have 1 unknown, 4 variables. That means that to solve for 1 missing variable, you have to be given 3 other things. So there are other ways, other problems that we could ask, but I'm not going to do that. I'm simply going to ask for the pH. That means that you're only going to have to be able to solve for the hydronium ion concentration. So let's do a problem. Calculate the pH of a buffer made by adding sodium bicarbonate and sodium carbonate so that at equilibrium, these are the concentrations of each of the acid and the base, and here's the Ka. So to base everything on the acid, which one is the acid? This has no acidic hydrogens, this has 1, so this is the acid. So I dissolve that in water. Here's the conjugate acid and the conjugate base. Then I need the equilibrium constant, which is products over reactants. Leave out water because it's a pure liquid. And then I need to get the pH. So that means I have to algebraically solve for the hydronium ion. So I did that right here. And now it's just a matter of plugging everything in and crunching the numbers. So here's the Ka, here's 2 concentrations. I crunch the numbers, I get this. This is the concentration of the hydronium ion. And to get the pH, all I do is take the negative log of that value. So I get pH of 10.252. So we can get a few more things for understanding from this problem. Notice that these 2 right here are the same concentration. This is maximum buffering capacity. So you can have a whole lot of the conjugate acid, a whole lot of the conjugate base. You're going to be good at buffering both acid and base. But mathematically, look what happens when these are the same. That becomes 1. Now the hydronium ion concentration is equal to, oh my God, the Ka. And if I were to take the negative log of this and the negative log of that, what do I get? I get the pKa. So now the pH is going to be equal to the pKa. So why is that important? Say, for example, I want to buffer a solution at pH of 9. I can go through a list of pKa values for the acids, and I'm going to be finding an acid with a pKa close to 9. So now I know if I take that acid and its conjugate base and I make a 50-50 mixture of the acid and conjugate base, the pH would be around pH 9, to be equal to the pKa. If I wanted to buffer at pH 9, I'm not going to use an acid with a pKa of 2. So just to summarize a few things, for a weak diprotic acid in water, so notice only one hydrogen comes off, okay, because that's the way it works. And then the equilibrium is simply the Ka. So here's products over reactants. And a couple things that we can get out of this. This ratio right here is the buffering capacity, and it's best when that's equal to 1. This right here gives us the pH directly. And if this number is big, that means that there's a lot of products. That means that the acid is a stronger acid. If this number for Ka is small, that means that you mostly have reactants left over. It's a pretty weak acid. And also, for a diprotic acid, here's the acid, here's the base. I know that because I can watch where the hydrogen ion goes. It goes from the acid to the base. And then, here's how I would get my products. But how do I know which one is the conjugate acid and the conjugate base? Again, I have to look where the hydrogen goes. It goes from hydronium ion to this in order to get back to what the reactants were. So that means that this is the conjugate acid and that's the conjugate base, as we see over here. So here's another one. Calculate the pH of a buffer made by adding sodium bicarbonate and sodium carbonate. And then you have these values at equilibrium, and here's the Ka. So I base everything on the acid. So hydrogen carbonate is the acid. So there's the reaction in water. Here's the equilibrium constant. I solve for the hydronium ion, and then I simply put in these values. So here's the concentration of the hydronium ion, and the negative log of that is 10.553. So what did I do between this problem and this problem? Here, I have the buffering capacity equal to 1. And then I change the buffering capacity. I have twice as much of the weak base as I do the weak acid. And did the pH change? Well, yes, a little bit. It went from 10.252 to 10.553. So does the pH of a buffer change? Yes, it does, but not as much as it would in water because it's buffered. In the next problem, I switch these around. So now I have twice as much of the weak acid as I do the weak base. And you can see the pH goes the other direction. Then, this last problem right here, I threw the buffering capacity way off. This is 1,000 to 1 difference right here. And does the pH change? Yeah, fairly drastically. Now it's moved about 3 pH units. So it's not a very good buffer at this point. So let's do another one. Calculate the pH of a buffer made by adding hydrogen, whatever this is. And if you look carefully, you'll see that, well, that's the acetate ion. So this is acetic acid. This is sodium acetate. So this is the acid. That's the base. So I take the acid, I put it in water, and then it's products over reactants. And then in this case, they're giving me not the Ka, but the pKa. So I have to convert into the Ka, and now I have everything I need to plug into the expression. So the negative log of 3.6 times 10 to the minus fifth turns out to be 4.444. Okay. So here's another one. Calculate the pH of a buffer made by adding 0.1 moles of sodium dihydrogen phosphate and 0.2 moles of sodium hydrogen phosphate to a total volume of 1 liter, and you're given the pKa. So which one is the acid? This has 2 hydrogens, that has 1. So this is the acid. I put it in water, 1 hydrogen comes off. Here's the equilibrium constant, products over reactants. I take the pKa, convert it into the Ka. So I solve for the hydronium ion, plug in all my numbers. There's the concentration of hydronium ion. The negative log of that is 7.501. As we'll see in a little bit, this is one of the most important buffers in your blood. So let's do a couple of examples here. What happens to the pH when you add 0.01 moles of HCl to 1 liter of water? Now water is at pH 7 and it's unbuffered. Okay, so here's what happens. It's complete ionization. So I'm adding 0.01 moles of the acid. So what is the pH of 0.01 moles? Is pH 2. So the pH of water dropped from 7 to 2, that's 5 pH units, because it's not buffered. But what if I would add that same amount of acid to 1 liter of this buffer up here? What would change? And I'm not going to ask you to do this on a problem, on an exam or anything. But what happens if I have a weak acid and a weak base under these conditions? If I add HCl, I'm adding 0.01 moles of hydrogen ion. I'm going to take, it's going to convert the hydrogen phosphate into dihydrogen phosphate, because that's what happens, right? So that means that the amount of weak base is reduced by 0.01 moles, and the amount of weak acid is increased by 0.01 moles. So all I did was take these same values up here and either subtract or add 0.01 moles. I recalculated the hydronium ion concentration, take the negative log of that, and you can see that it dropped from 7.501 to 7.437. Not much of a pH difference because that's a very well buffered solution. The ratio is about 2 to 1. Not the best buffering capacity, which would have been 1 to 1. So this is in a red box. I don't want you to memorize how to do this math or anything, but I'm going to show you the derivation of the Henderson-Hasselbalch equation. So here's the equation that we were using to solve all of our buffer problems, right? If I take this equation and I invert it, I just do the 1 over x function, I get this. Then if I take the logarithm of that, notice that the log of multiplication becomes addition. But now if I look at this, this is the definition of pH. This is the definition of pKa. And this is just what it is. So all we've done is taken this equation that we were using and convert it into a different form using inverse log. Most textbooks want you to memorize this equation. And I'm sorry, for me, I am against using this equation and having students memorize anything. like as soon as you have an equation to memorize, it's like, oh, forget about all that other basic science stuff we learned. So we're just going to be using this equation, and you can see how we do it. It's very straightforward, and we're using all the things that we had learned in chapter 19 and reinforcing them in this chapter. So to me, chemistry by itself is not that interesting. But when you apply chemistry to biology, I think it's unbelievably interesting. So here's an opportunity to do that. So the pH of human blood is about 7.40, plus or minus 0.05. And if you're out of that range, then you are at risk of all kinds of issues, including being dead and stuff. So blood is an extremely well buffered solution. Okay, and if you look at blood in general, there's basically 3 really important buffers. The rest are less important. The first one is called carbonic acid. And previously in the other edition, I put incorrectly referred to as bicarbonate. And here's the reason why I would say that. You're looking for a pH of 7.4. So what would be important as a buffer would be a pKa with 7.4. So carbonic acid has a pKa of 6.4, which is 1 pH unit off. But look at bicarbonate. That's about 3 pH units off. So the most important buffer at 7.4 would be carbonic acid. So in true form, I take carbonic acid, I put it into water, and then I see the conjugate base and the acid. And if you look in a real person, it's pretty well high concentration, so 25 millimolar, so 25 times 10 to the minus 3 moles per liter. So you have about a 10-to-1 ratio of the weak base to the weak acid. That's about the approximate buffering capacity. So where does this buffer come from? Well, you eat foods. For example, here is glucose. You breathe in oxygen, and you produce CO2 and water. So yes, you exhale this, but you don't directly exhale it. CO2 is created within your body, within your cells. So it can't escape. So it's a non-polar molecule forced to dissolve in a polar molecule. So that basically forces it to cause a chemical reaction where you form carbonic acid. And what does carbonic acid do? Well, it ionizes to give you hydrogen carbonate and hydronium ion. As we'll see in a few minutes, of the 3 buffers that are important, this is the only one that you control. You control this by your breathing rate. You can control how much CO2 is in your body. So then another important one is dihydrogen phosphate. So notice that dihydrogen phosphate has a pKa of 7.2, close to 7.4. Hydrogen phosphate is several pH units away, several orders of magnitude away from where it should be. So taking this weak acid, putting it in water, so that becomes the conjugate base and the weak acid. So this ratio here is still pretty high. It's about 1 or 2 to 1. And so in the body, dihydrogen phosphate is an extremely important buffer. This is one of your electrolytes, and one of the reasons why you need very good electrolyte balance. And the third and last one we'll talk about are proteins. So it's a little bit more difficult, so I'm going to make some simplifications here. But here is the acidic form. So this right here is protein is made up of amino acids. So here's the amino group that's been protonated because it acts like ammonia, a base. Here is the carboxylic acid, which is protonated. It's basically about the same strength as, similar to acetic acid. So the pKa for the carboxylic acid is about 4.1. The pKa for the amino group is about 9.4. So here's what can happen, how it can act as a buffer. So here is the base form, here is the acid form. If I look at the ratio, it's very close to 1-to-1. So excellent buffering capacity here. Now, one thing that we often do in organic chemistry is when we have a molecule with more than one acidic or functional group on it, acidic or basic group on it, we take the average of the pKa's. In this case, the average would be 6.75, which is not that far from 7.4. So another reason why proteins are important blood buffers is because they're just extremely concentrated. Protein concentration in blood is about 72 milligrams per mil. And the most concentrated protein drink you can make from commercial bodybuilding powders is about around in there. So here's 72 grams per liter. Here is, close to, what is that? 20, it's about 20% of that. So in other words, blood is extremely high concentration. Here's one, Synthesis claims to be about 23 times that of concentrated in blood. So of course, that's why vampires are so strong. If a vampire wanted to be really, how do you say, get the best nutrition possible, they would get their blood from bodybuilders. So now here's how it works. You cannot change the concentration of protein in your blood or of dihydrogen phosphate in response to changing your blood pH. The only thing you can change is your breathing rate. In other words, the hydrogen carbonate one. So your blood, the pH is monitored by the central nervous system, and that controls your breathing rate. So a lower pH, that means a higher hydrogen ion concentration is going to cause an increase in the breathing rate. And a higher pH or lower hydrogen ion is going to cause a lowering in the breathing rate. Here's a couple of things. If you hold your breath for too long, you're going to pass out due to what's called respiratory acidosis. Okay, so what happens is this. Here's the equilibrium over here. You're creating CO2. It combines with water to form carbonic acid, which then is a weak acid, then ionizes, right? Here's what affects the pH. If you hold your breath, that means that you're creating CO2 faster than you're getting it out of your body. So the stress, which I always put the stress on the bottom, is that you're increasing the amount of CO2. And the result, which I always put on the top, is going to be this. It's common sense that if you add more reactant to something at equilibrium, you're going to get more product. So that means that you're going to shift the arrow in that direction. So once you identify the stress, you identify which direction that arrow is going to go. It either goes towards forming more products or forming more reactants. There's no other choice. So if I put more CO2, I push the reaction this way, now I'm making this concentration go up. When that concentration goes up, I push it this way, and what happens to bicarbonate? It goes up, and hydrogen ion goes up. And that causes a lowering of the pH. So if you hold your breath long enough, you will pass out, and then your autonomic nervous system takes over and says, hey, stupid, you forgot to breathe, so we don't want to die here, so we're taking over. And then you start to breathe again. Unfortunately, if you're underwater when that happens, then you'll drown, right? Pass out underwater. What happens if you hyperventilate? If you hyperventilate enough, you will pass out due to respiratory alkalosis. So, what's going on here? With hyperventilation, you're getting rid of CO2 faster than your body is making it. So the stress is that you're removing CO2. So if you're removing one of the reactants, the reaction shifts this way in an effort to try to replace it. So that means hyperventilation, you're going to reduce the concentration of hydrogen carbonate. To counteract that, the reaction goes that way to try to replace it. So bicarbonate goes down, hydrogen ion goes down, and what happens is the pH goes up. So this is a problem with many people have died from what's called shallow water blackout. They hyperventilate, thinking that that's going to let them stay down a couple of seconds longer underwater. So they hyperventilate, they start going down, and they pass out. Then their autonomic nervous system takes over, tells them to breathe, and they drown. Anyway, a couple of things here. Say you're running away from a predator. You're running, you're getting out of breath, and all of a sudden you can't do anymore, you fall down, you might even pass out. What's going on? You produce so much CO2 that you forced your reaction this way, you are in what's called respiratory acidosis. What about people who have panic attacks? So they've got rapid breathing, shallow breathing often, but rapid breathing. What they're really doing is getting rid of too much CO2, and they will pass out. So what do you do to a patient like this is you have them breathe into a paper bag. So they're rebreathing the CO2 that they exhaled, trying to keep more CO2 into their body to maintain their blood pH. So these two words, respiratory acidosis and alkalosis, are also correlated to what's called metabolic acidosis or metabolic alkalosis. And those are due to chemical reactions in the body of metabolism. So for example, people can experience changes in their pH because of diabetic attacks, drugs, people take drugs and things like that. So yeah, that'd be more like metabolic considerations. Anyway, maybe what I'll do is just finish this lecture. So, other organs in the body besides the lungs are also involved in the regulation of pH. So you have the interstitial fluids around the cells that are in equilibrium with the blood. Those buffered fluids contain similar buffer systems, often referred to as the bicarbonate reserve, which is in this box over here. And then you have your kidneys can acidify urine, and they can excrete hydrogen ion. At the same time, they can also retain bicarbonate in the blood. So if this would raise the pH. Getting rid of this would also raise the pH. So the kidneys are really important in helping your body maintain its pH. So somebody with decreased kidney function is going to have a harder time maintaining their metabolic pH correctly. So another thing to be considered of. So the human body, say it has about 15% body fat, is about 62% water by weight. So it's kind of surprising when you look. Bones are about 50% by mass water, adipose tissue about 10%, lean muscle about 73%. 150-pound person has about 93 pounds of buffered solution. So then, that's the end. Really, it's only 6 pages in chapter 20. But I put a couple of things here that might be helpful if you take another chemistry course. So what happens if you take a strong acid and a strong base? Okay, one directional arrow goes 100%. These are titration problems. If I take a strong acid and put it in water, 100%. So 100% ionization, I get a Ka that approaches positive infinity. What happens if I take a weak acid and a strong base? Well, strong base is enough to make it go to completion. Those are titration problems. What if I take a weak acid and put it in water? Well, no, that's an equilibrium, and I can measure the Ka. The equilibrium constant is not huge. Okay? Might even be small. What if I take a weak acid and a strong base? So a strong base is enough to pull a reaction all the way to completion. And again, it's a titration problem. If I take a weak acid and I put it in water, so notice I'm doing a slightly different one over here, then I get an equilibrium constant. That means I can use it in a buffer problem. And what would happen if I took sulfite? If I took sulfite and put it in water, I would make water act as the acid, and I would produce hydroxide ion. In other words, it would act like a base. And this is called hydrolysis. So here's a few other things. One of the things that I have in chapter 19 maybe, is we calculated the concentration of water from its density. So it's about 1 gram per mil, about 1,000 grams per liter, and 18 grams per mole is just molar mass. That's how we get the 55.5 moles per liter. And in most equilibrium problems, we leave out that value because it's a huge value that doesn't change very much. Here is the definition of Ka in the most simplest form that I can put it in. Again, it's simply products over reactants. Here's the definition of Kb. Notice that I'm taking the conjugate base here and putting it in water. So here's the simplest definition of Kb. What happens if I multiply Ka times Kb? Notice that, HA cancels out, A minus cancels out. What I have left over is this. Oh, but wait a minute. I remember that being equal to Kw, which was 10 to the minus 14th. In other words, Ka times Kb is equal to 10 to the minus 14th. Now, what if I take that relationship? Okay. So I did the inverse, and then I took the logarithm of it, and what do I get? Oh, pKa plus pKb is equal to 10 to the 14th. So now, we don't really need these equations in this course, but if you're taking another higher level course, if you got the pKa, you can easily calculate the pKb. If you got the Ka, you can easily calculate the Kb of its conjugate base. And here's the one that drove me nuts as an undergraduate, because it was just so logical to me that the pKa for water should be 14. So, but you look it up online in a textbook, the pKa is 15.7. Like, what? Here's the reason. They're using heterogeneous equilibrium, which means they're including water in its calculation. So in other words, they teach you about equilibrium. Now you're using homogeneous equilibrium, and you think that's the major one that they're using. Then all of a sudden, they tell you the pKa for water using heterogeneous equilibrium. It's kind of irritating. Anyway. So here's some potentially funny cartoons I thought you might enjoy. Anyway, I'm going to stop here. And if you have any questions, you can always email me. And let's see. And I'm going to end the meeting, and I'm going to get this posted sometime today. Okay? You guys have a great day.